Hello students, welcome back. Let's go back to section 5, and section 5 is basically all about this formula, the last line here. Oops, I went a bit too much. And this part gives you the solution of the homogeneous equation. And that part is a particular solution. Okay, here we go. What is the matrix expression of this thing? So I1, y1 prime and y2 prime. And then the matrix is, I need just y2, so 0, 1, and -1, 0, and y1, y2, plus t minus t. And this time there's no initial condition, so I'm not going to worry about y star part. In the end, I'm going to put y star as C1, C2 and go from there. Okay, this is my matrix A, and this is my non-homogeneous part F. That's my Y. All right. Here's a matrix form. Is everybody happy? Okay, let's go to homogeneous equation, or the solution of the homogeneous equation, that thing. Nothing is specified, so I can assume no, let's not use y star expression. Let's just do C1, C2. Let's do it like this. Now, how do you solve the homogeneous equation? It's this part, isn't it? So we need e to the a t power times this. That's the blue solution. So if we find out this matrix exponential, then we are through. How do we find this matrix exponential here? As a matter of fact, we have found out already twice. Here we had it. This was using the brute force method, doing all those computations, and then put everything into Taylor's Maclaurin series expansion, and then somehow, luckily, we got a pattern, and then we got this matrix exponential. Not pretty, but it worked out. Of course, there was a little better method. Here in section 4, we did it this way. I think this problem. Yes, indeed. Find out the resolvent matrix, Si minus A, and then take the inverse using the inverse matrix formula for 2 by 2 matrices. Turned out we have S squared plus 1, so that's easy. You can look up this Laplace transform table in page 123. Here you end up with cosine of t, sine of t, negative sine of t, cosine of t. A little bit more elegant method. In any case, we have it. So that's a matrix exponential and times C1, C2. So the answer should be C1 cosine of t plus C2 sine of t. And here we have negative C1 cosine of t plus C2 sine of t. That is the solution of the homogeneous equation. Okay, we did all these here. All right, we have it. Now let's go to step 3, and step 3 is this. We need e to the a t minus u. So a t minus u, and this one is e to the at power. So here, in place of t, I'll have to replace everything by t minus u. Is everybody with me here? Why I'm replacing t by t minus u? So this is the exponential, matrix exponential e to the at, but in place of t, I have t minus u, so I take appropriate substitution. How about f of u? Well, f of t is given like this, t negative t, but I have to change this to u, so this is going to be u negative u. We have e to the t minus u power, f of u. So we have these two. So if you multiply those two, then I'm going to get, let's see, e to the a t minus u times f of u is equal to this matrix multiplication. And then basically what we want is this integral computation. Let's see, where's the integral? Yeah, here's the integral. And 0 from t. And then du. So basically I want same kind of integral here. 0 to t du. Do the matrix computation first, and then I'm gonna get a column vector, 2-1 column vector, and then take the integral each time, and then you're gonna be done. Tedious it may be, it can be done like this. Okay, basically we want this integral computation, what's happening with this window, and then e to the at minus u power, and then times f. If you calculate, we get this, and of course this is tedious computation, so as you can see, I use Mathematica command for that. And then now that I got the integrand, calculate the antiderivative. And that is the particular solution. Again, here, this was tedious computation, so I think I used Mathematica command here. Yes, I did. So a lot of computer algebra system here. Otherwise, we have some out-of-control computation here. So if you add up this and that, that's going to be the general solution. So this part is homogeneous part. That part is C1, C2. And this part is the particular part. That one does not have any undetermined coefficient. I think you can stop here, but I decided to go just a little bit further, simplifying, and then rewrite these coefficients instead of C1, C2, where C1 plus 1, C1 minus 1, those kind of things. I just named those as A, B like that. A little bit more elegant form, I guess. And then I can check everything. Yes. Okay, all right. So there goes another problem. Now, do you have time for another problem? I don't know. I may not, but let's try anyway. So basically, this is what we are going to do. Get the homogeneous part, and that's basically for exponential. And then here, matrix exponential and times f of u, the non-homogeneous part, and then take the integral. Now here in this particular case, y star is 2, 1, do you see? And also t0 is 1, so in this case we have to do this. 1, and then this will have to run from 1 to t, because we have 1 here. Make sense? Here's a matrix form. All right, it corresponds to this, and also the initial condition here. And copy and paste this thing. And then the homogeneous equation. So forget about this one and work about this one. But then again, make sure you're getting t minus 1 here, not t minus 0. Let's see, t minus 1. Okay, before finding this one out, let's just find out e to the at power, and later on you can replace t by t minus 1. Okay, here we go. Resolvent matrix, so Si minus A and S minus first entry, 0 minus 1, 2, and 3, 0 minus 2, 1, and 3, and S minus 2, 2, and 3. With this matrix, we get that. And then we have the inverse matrix formula, 1 over AD minus BC. And we have to switch the principal diagonal and negatives to the other. And if you simplify all this, you're going to get 1 over s squared. Oh, that's nice. And consequently, we get some decomposition by partial fraction, which, for a change, I didn't need computer algebra system this time, because the denominator was so simple. I could handle it without computer algebra system here. So, you can take the Laplace inversion, and this is what you get. You see, 1 over s will give me 1, and 2 times 1 over s squared, that's t, and 1 over s squared, that's t, and so on and so forth. And now, from here, mark me, I want e to the a t minus 1, so I have to substitute each t here in this expression to t minus 1. So this expression here is for e to the at. And this one here, where all the t's are replaced by t minus 1, is this one, e to the a t minus 1 power. And that times y star to 1 and do your computation. There goes your blue solution, the homogeneous equation, the solution of the homogeneous equation, YH. Too fast? Well, you can stop this playback and then study over. The resolvent matrix and this kind of computation is not bad at all. The Laplace inversion is standard. Just look up page 123. But this may be a little bit new. I want a t minus 1, so replace t by t minus 1. And then just the routine computation. And this is a blue solution, this one here. Now, so much for the homogeneous part. Let's go to the non-homogeneous part. Here we have this e to the at power. That one. So over there, I have to replace this t by t minus u. And that's what we did. T minus u, t minus u, t minus u, t minus u from there. And then f is 1 over t, 2 over t. So replacing into u, I get 1 over u, t over u. So all I have to do is to do this matrix multiplication, simplify, and then take the integral. Elementary but tedious computation follows. And then take the integral. Again, elementary but tedious computation. In the end, we have 1 plus 4t, 2 minus 8t, the t part, and then the u part is going to be a logarithm, so log of t there. And then you cannot plug in 1. As you can see, you have logarithms, so you cannot plug in, it doesn't go to 0, so you have to plug in 1. And it's no coincidence, you're beginning from 1, and then you end up with logarithm here. If you start from t equal to 0, it probably wouldn't have made any sense. Anyway, plug in u equals to 1, so we get this kind of expression, because log of 1 is 0. Anyway, we get that, and that's my red solution. Putting those two together, this is one you got before, the homogeneous part, and this is a particular solution from the non-homogeneous part. Add them together and you get the final solution. That concludes section 5 here. We ended up with a lot of problems, really a lot of problems on non-homogeneous linear systems with constant coefficient, but only up to 2 dimensions, y1 and y2. What if we have more functions? For example, what if I have a system of 15 equations? And basically we do the same thing. We take the matrix exponential, same idea, except that the decomposition by partial fraction is going to be humongous because we have to do the same thing 15 times 15, which is 225 times. Okay. And then we got a homogeneous solution. And then from that matrix exponential, replace t by tu, matrix multiplication. All those can be handled by computers completely algorithmic fashion. So yes, all these things make sense. It's just that we do 2 by 2 only because we can handle without using any kind of, with minimal use of computer algebra system. And we learned, as a matter of fact, everything that we need to know about arbitrary dimension, to tell the truth. It's just that I'm not going to write that kind of problem because they're just too tedious, elementary but tedious. As far as the theory is concerned, we're through. Any kind of linear systems with constant coefficient, we completed. That's a big accomplishment we had. Okay, so much for lesson 14, and lesson 15 will be mostly optional. Thank you.